Actually, before we stick some more numbers in, I want to mention something that you might have seen before. Let's imagine that you are standing in some water. Maybe this is a lake or a stream or something like that. And you are looking at something under the surface of the water. Maybe there's a rock on the ground or something like that. So here's a rock lying on the ground. Here's the ground. Here you are standing there. Here's the surface of the water. My question is, where do you see the rock? Let's remember, you see something where the light enters your eyes. You trace those rays back as they enter your eye. Your brain traces those rays back, and that's where you see something. Remember, we talked about that when we were talking about images formed by reflection. Well, where do you see the rock? Well, how does the light from the rock get to your eye? Does it travel on a straight line into your eye? No, because it's going from water. The light is going to go from water into air. It's going to refract at the surface. Will the light refract toward or away from the perpendicular? You're going from water into air. That's from an index of 1.33 to an index of 1.00. The light is going to refract away from the perpendicular. So how is it going to go from the rock to your eye? Well, it's going to go something like this. It's going to come up to the surface, and then it has to refract away from the perpendicular. So here's the refraction, and the light is refracting away. And then another ray nearby might do something like that. And those are the rays that actually enter your eyes. Where do you see the rock? Well, you see the rock where your eyes trace the rays back that are actually going into your eyes. So you trace these rays back, and they are coming from this direction, and you will see the rock over here. That's where you actually see the rock as being. Not down here, but up here. Notice that this rock, this that you see, is closer to the surface than the real rock. What does that mean? Well, it means if this is on the ground, looks like it's on the ground, when you look in the water, it looks shallower than it really is. Maybe you've experienced this. You come over to a body of water, a stream or a lake or something, and you're going to step in the water, and you step in and, oh, it's actually much deeper than you thought it was going to be. Well, the reason is right here, because when you look at the bottom of the water, it is closer to the top of the water than it really is. And so when you step in, it turns out you've got to step in much further down than you thought. Very, very interesting result. Now let's stick in some more numbers. Let's imagine that we have a ray in the water with an incident angle of 55 degrees. Again, remember, n in air is 1.00, n in water is 1.33. Let's figure out what is the refracted angle in the air. I'd actually like you to work on this before I stick the numbers in. So if you want, why don't you turn off the video, see if you can figure that out, and then when you're done, turn it back on again. I'll assume you've given it a try. Let's see, let's stick the numbers in. What do we have? We've got n1 sine theta 1 equals n2 sine theta 2, or n air sine theta air equals n water sine theta water. We've got 1.00 times sine theta air equals 1.33 times sine theta water, which is 55 degrees. So sine theta air is equal to 1.33 sine 55 divided by 1. Divide that out, and we have 1.09. So theta air is the inverse sine of 1.09, which is, I would imagine if you tried that on your calculator, you can't do it. There is no angle that will give you a sine that is larger than 1. Well, that is very strange. What is this telling us? It's telling us that this ray will not be refracted. Well, if it's not refracted, what does it do? Well, remember in the first demonstration I showed you, not only are rays refracted, but what else are they? They are also reflected. In this case, none of the ray is refracted, but it is all reflected. So it is reflected back into the water. the ray stays in the water. This is a very, very interesting result. Oh, and just by the way, what's the angle? Well, we know for reflection it's going to, whoops, that's supposed to be 55 degrees. We have an angle of reflection that's equal to the angle of incidence. So we know it's going to reflect at 55 degrees. This is a very, very interesting result where all we have is reflection. This phenomenon is called total internal reflection. What's going on here? Well, let's think about what we already talked about. When we have a ray in a higher index going into a smaller index, we know the ray is refracted toward or away from the perpendicular. Away. So we know a ray coming up here is refracted away from the perpendicular. So something like that. Now, what if we increase? Let me enlarge my my rays here a little bit, make it a little bit easier to see. So here we've got a ray coming in and refracted away from the perpendicular. What if we increase our angle in the water a little bit? Well, we need to increase the angle in the air a little bit. We increase this a little more, increase this a little more, increase this a little more, increase this a little more. Eventually, we will get to such an angle that the refracted ray is refracted right along the surface of the interface. In other words, the refracted angle is 90 degrees. What if we increase this angle more than that? Well, this angle cannot be more than 90 degrees and come out into the air. The only thing that can happen is it can reflect inside the material. That's why this is called internal reflection. This only occurs inside the medium where the ray is starting, and it will only occur when we are in a medium with a larger index than the other material. If this were a larger index than this one, the ray would be refracted toward the perpendicular, and we would have no problem increasing this angle all the way up to 90 degrees. It's when this ray is refracted away from the perpendicular that this ray will end up at 90 degrees before this one, and we cannot increase this one any more. Total internal reflection. Well, at what angle does this occur? What's this limiting angle? The angle when we get a refracted ray of 90 degrees. Well, let's stick that into our equation for refraction and figure that out. Let's imagine we have this incoming ray at this angle that gives us a refracted angle of 90 degrees. Now, this particular angle is called theta sub c. Theta sub c is the critical angle for total internal reflection. So let's see, what do we get? How do we solve for this? Well, we know that n2 sine theta c will equal n1 sine 90 degrees. Sine of 90 is 1, so n1 times 1 is just n1. Dividing both sides by n2, we have sine theta critical is equal to n1 over n2. There we go. That's how we can find theta critical. Take the inverse sine of both sides. We have theta critical as the inverse sine of n1 over n2. Let's stick our numbers in here. n1 was equal to 1.00, n2 was 1.33. For an air-water interface, we get a critical angle of 48.8 degrees. What does that mean? When a ray is at 48.8 degrees in water, the refracted ray is at 90 degrees in the air. Any ray at an angle larger than 48.8 degrees will not come out into the air. But what angle did I give you? I gave you an angle of 55 degrees, which was larger than 48.8. That's why we cannot get any refracted light at a 55 degree angle. Very good. Now keep in mind that in order to have total internal reflection, we have to have a ray that is going to refract away from the perpendicular, which means the ray must be in a larger index reflecting off of a smaller index, which means the upper index must be smaller than the lower index. N1 must be less than N2. Obviously, if you try to take the inverse sign of N2 over N1 and have a number larger than 1, you can't do it. So you can only find a critical angle if a ray is in N2 reflecting off N1. Something to keep in mind, notice for this equation, the ray starts out in the index that's in the denominator. The ray starts out in the material with the index in the denominator. And N1 must be less than N2. We can only have total internal reflection for light in water reflecting off air, not for light in air reflecting off water. Very good. Can this be used for anything? Well, yes, it can. Let's imagine we have a long tube of some material that's made with a large index of refraction, and we send a ray of light into the tube, close to the angle of the axis. So, in other words, with an angle relative to the normal line of the side of something that's going to be large. Well, what's going to happen? This ray is going to come in, eventually it's going to bump into the side, but that's going to be at a large angle to the normal line. What's it going to do? Well, as long as it's large enough, as long as that angle is larger than the critical angle, we're going to have total internal reflection. That ray is not going to come out, it's just going to reflect back inside until it hits another side. And as long as that's at a large angle, it will reflect again and go down the tube. And this ray will just continue to go down the tube, reflecting off the side. As long as the tube is not bent at too large an angle, the ray will just keep bouncing off the side and travel down the tube. Well, does this sound like anything familiar? Anything you might have heard about? Well, this is the basic idea behind fiber optics. It's the phenomenon of total internal reflection that allows fiber optics to work, that keeps that light traveling down the tube without refracting out the surface. As long as this material is optically pure, that ray will travel a very, very long distance. Now, if there's any kind of material scattered in here, or if the surface is not optically smooth, in other words, smooth relative to the wavelength of the light, then some light will be lost, but as long as the material, as long as the tube is very smooth and optically pure, that ray will go for a very, very long distance. We can actually demonstrate this. I'll do it a little bit and then I'll turn the lights off and hopefully get a little better view. Here I've got a plastic tube and a green laser, and what I'll do is I'll put the laser in one end here, and what you'll notice is although you don't get a perfect spot coming out the front, I think you will notice that you get a bright green spot at the front. And we can actually see that if I shine it on the whiteboard, you can actually see a little green spot there for the laser coming out, even though that laser had to go up and around and then come out the front this way. Now I'll turn the lights down and we'll see if we can see it a little bit better. There we go. We can see the laser going in and again coming out the front, and I can shine it on the screen and we definitely see a green spot coming out the front. Very good. Here we go, we've got the laser going in. You might even be able to see the laser actually traveling down the tube. I can see it, I can actually see the beam inside, but you might not be able to see that. We can shine it on the board and we definitely see a very bright green spot coming out the front there from the laser bending around. Okay, very, very good.